To attain meaningful breakthroughs in innovation, engineers need help manufacturing their most ambitious designs. But many of today's conventional manufacturing technologies often have strict design limitations, require long lead times, or find it difficult to reliably scale production. Velo 3D helps engineers move beyond those limitations with its unique, fully integrated approach to metal 3D printing. By combining hardware and software into one fully integrated solution, Velo 3D simplifies the additive manufacturing process while enabling unprecedented levels of part consistency, quality, and repeatability. With this design freedom, engineers can focus on designing parts optimized for performance, not manufacturability, enabling greater innovation and speed to market. From 3D printing complex one-off parts to scaling vast supply chains, Velo 3D can help you print the parts you need without compromise.
Hello and welcome to today's webinar hosted by TCT Magazine in partnership with Velo 3D, where we will be discussing how to implement scalable manufacturing strategies with advanced metal additive manufacturing. I'm Sam Davis, the Group Content Manager at TCT, and for today's webinar, I'm going to be joined by Gene Miller, the Director of Technical Sales at Velo 3D, and Michael Harsh, Technical Sales Engineer at Velo 3D. Throughout the webinar, Gene and Michael will detail the roadblocks to successfully scaling metal additive manufacturing and how the fully integrated metal AM solution offered by Velo 3D overcomes those challenges. They will also discuss how standardized print parameters can accelerate design innovation and how fleet-level calibration helps to combat print variability. I'll be handing over to Gene, who will start the presentation today.
Let's get started and talking about the main topics here. We really want to address, with so much opportunity in today's world where there's so many parts to print or manufacture, why are there so few additive manufacturing applications actually being produced in real world applications? And I think it boils down to this technology, even so, exists for 30, 40, 50 years. It's still in its infancy when compared to casting and other legacy manufacturing processes like machining and casting that have been around for decades or centuries, even millennia. Casting's thousands of years old. So how do we bring the additive manufacturing process to its next stage in life of having a reliable, repeatable process so that we can treat it as a scalable production process? Next slide. And fundamentally, the challenges that are inherent with the metal 3D printing or additive manufacturing processes are we need to generate repeatable material properties and reliable geometric accuracy, not just once. We need to do this many, many times on different machines from different suppliers. And we need to do that in perpetuity, year after year, without machine drift. And there's really challenging implications that go along with that, that Velo is trying to bridge the gap on a lot of those limitations with the current manufacturing solutions. Next. So the challenges that we see in the industry today are printers are like snowflakes. We think they're very unique. And the problem is that oftentimes we must tweak or change or modify print files for each machine. So if I print one part on machine A and I want to print that same part on machine B, I need a second print file. And that's very difficult as you scale in production when you have a unique print file for each print that you're going to perform. The machine itself is a challenge because we have different ways of manually calibrating these machines with third party or hardware that needs to be installed in the machine to quantify, and it relies on users that might be trained differently or have different attention to detail. So the result in these calibrations is essentially variable because it's based on human input. And then each supplier, as it exists in the world today, likes to create its own process. They can push for throughput on a lot of these processes, or improved surface roughness on downskins, things like this. And each supplier likes to consider this their own IP, which is great for them. But when you look at the grand scheme of how that scales, supplier A isn't going to share their parameters with supplier B because they're inherently competitors of each other. So having these many processes from many suppliers is a real challenge, or a stopgap when it comes to scaling for production. This high level of variability is a huge stymieing factor when we try to create generalized and repeatable scalable processes, and is a big gap between where we are today and where we need to be in treating additive manufacturing like a scalable manufacturing production process like it needs to be. Next. So how do we achieve part qualification? Velo does some very unique things. We are, you can go to the next slide. We are taking the factors of error out of the equation, and a lot of that comes from the process and how it's prescribed. And we have a generalized software applying these processes again and again in an automatic approach, so that the user doesn't have to be as involved with applying specific processes to each part that they're trying to print. The machine itself that we manufacture and produce is built in with automated machine calibrations, and the user can it's not a one click, it might be a 5-click automatic calibration on the machine that can deliver repeatable results, not reliant on any user or training or anything like that. So the print file then is another area where we're eliminating that variability. That one single print file that is generated from our software can be used on machine 1, machine 2, machine 3, and it doesn't matter if it's at supplier 1, supplier 2, or supplier 3. You can use the same print file at different locations and expect that same result. The integrated process monitoring is another key factor in assuring quality of your printing process. We have built in health checks and monitors to report any anomalies throughout the print, as well as machine health. These automated calibrations are performed before printing and also captured in our data software. And then another important factor here is generating pedigree data with third-party or regulatory certifying bodies. Large, robust data sets with these repeatable material properties, so that engineers can reliably design based on that design criteria, is really important to share with designers when they're optimizing parts for their application. And this really takes a lot of the variability out, like I'm saying, and we don't have to go back to the drawing board every time we want to do this again and again. So it's instead of starting all over again, you can build on your first success. Next slide. So there's multifaceted of part qualification, and it starts with the material that you're producing. This starts with feedstock, goes into laser processes, and all of these things, like we're saying, the variability cannot exist to reliably produce parts. Having a common parameter that is locked down and unchanging, and the pedigree data that we can generate is important to rely on for designers. And with that, with variability comes the inability to scale in this case. The printer qualification, we're talking about automatic calibration aside from user error or variability is very important, and the process monitoring in situ in the building process. And then if you want to do it again and again from machine to machine, this is something that scales much more seamlessly than the existing approach of starting from scratch. Printed part, we want to make sure that the part that comes out of the machine is the same. And once we get to this point, we know we have this a similar machine running with similar or the same parameters, and we can expect that part to be repeatable. But it's another portion of the qualification aspect. And once you have that part, you still have to put it through a final qualification, and that might include something more like cyclical fatigue testing or application testing to make sure that the part geometry is performing properly. Next slide. So
yeah.
to take us into an example of where we're actually doing this, to prove that I'm not just blowing smoke, I'll hand it over to Michael here, and he'll take us through a great example of an energy, oil, and gas scalability study. Michael?
Yeah, thank you, Gene. Yeah, so this case study is really interesting, and it demonstrates a use case where we were able to exercise these qualification processes and procedures successfully, ultimately leading for a big OEM in the energy and oil and gas sector to achieve scalability with our additive manufacturing technology. So the company that we've partnered up with is called IIMI CCI. We've been talking to them for a long time, or been in touch with them for a long time, and it's a really interesting company, a big player in the oil and gas sector. They do a lot of things, but for metal additive manufacturing, we were particularly interested in a component that they are producing, which is called a drag valve or choke valve. And this is a very interesting part. As you can see in the picture on the bottom right, on the right side, it's a valve that controls the flow of fluids in upstream oil and gas applications. So this could be in an oil well, in a power generation, in nuclear plants, or chemical refinement. And all of these environments where these parts are being used are very harsh and have require very strict tolerances to make this part successful. So what is interesting about this part is, first of all, its complexity. So we have a lot of internal geometry, channels, complex flow passages that run through the part. And we consider this part to be high mix, low volume. So while there is a, let's say, basic design platform or design principle, how these parts typically look like, there are also a lot of different variants of this design, depending on the location where they are being deployed, or the specific application where they're being deployed. So this means high complexity, which by default is very difficult to manufacture conventionally. In fact, these geometries, if you want to make them conventionally, which they used to be manufactured by CNC machining and brazing, you have a very long and complex process chain, which is cost ineffective and also difficult to control with regards to part quality. And furthermore, if you think about that high mix, so a lot of different variants, but low volume for each variant, that also means that if you do them, for example, by CNC machining, you need a lot of tooling investment, a lot of fixtures investment. So all in all, it's not ideal for conventional manufacturing. So IIMI CCI, a long time ago, started to look into these parts and see if additive manufacturing is a viable approach to produce these parts. And they have been successful proving that you can build good performant design variants of these valves that are on par or better to the conventionally manufactured ones. However, and this is really now touching on what Gene mentioned, what IIMI's ultimate target was to create distributed supply chain. So scale up their production and being able to produce these parts, not just on one machine in one place, but produce them through different vendors that use different serial numbers of machines at different deployment sites, therefore being able to minimize the lead time, the logistics of getting these parts where they are needed. And this is where the problem lies with conventional or legacy AM. You can get a good part, but getting that part twice, or getting that part twice on 2 different machines or in 2 different locations, is a problem. There's always a struggle with poor part consistency and variation in key process variables and therefore mechanical properties. Furthermore, it's often difficult to be conformed to the regulatory bodies. So in this case, what we are talking about is API 20S. That's kind of like, if you think about aviation and aerospace, the FAA, so a set of specification frameworks or requirements that need to be fulfilled to make that part qualifiable. And basically, this schematic here now is reiterating or re-explaining what Gene mentioned. So as an OEM, in this case, IIMI CCI, you want to scale your production. So you always start with the first machine at your first supplier, and you create a print file that contains all of the process parameters, and these might be unique to that specific machine. Furthermore, there are other things to worry about. So how are my material properties of the powder material that I'm using? How are the key process variables during the build? All of that needs to be qualified, and that requires a huge amount of basically R&D money to make that happen. But of course, as IIMI CCI, they don't want to be reliant on one machine at one supplier. So the first supplier maybe brings in a second machine, but now the whole process has to start again because these legacy machines are not able to use just one fixed set of processing instructions in one fixed print file. No, you have to start with your qualification again. So again, you have that non-recurring expense to pay to get the qualification up. But the story doesn't end here. We said IIMI wants to create a network, a distributed supply chain. So a second supplier, a third supplier, a fourth supplier needs to come into play. But every time you have the same invest and the same hassle and ultimately resource and time consumption needed to qualify the part. And even if you manage to do that, there's still some sort of uncertainty whether this is still all good. So with the technology that Velo3D offers in additive manufacturing, we are able to get around that. And I want to share the story how we did this with IIMI CCI. So first, we produced the first production valve on a Velo3D Sapphire machine. And actually, you can see the build layout on the bottom right. And what we did here is you can see also a lot of coupons. So this is due to the API 20S framework, where I will talk about this a bit more in the next slide, but there are certain requirements as to which mechanical data needs to be tested and reported, and also which process variables during the build need to be documented and available for the regulatory bodies to make this qualifiable. So we built this part, we built it successful, and the next step was just flow testing in the lab. So checking if these valves that are produced additively on our machine can compete or can be compared to the conventionally and already qualified drag valves. And actually what you see here is two lines or two plots, but the fact that both of them are on top of each other shows that these Velo 3D printed drag valves actually were equal in performance to the conventionally manufactured ones. So at this point, IIMI said, okay, that's very promising. Let's deploy them in the field and see how they do. And now I want to take you through the timeline. So as I said, we started with the first proof of concept, the first article that was tested in the lab. Then about 3 months later, we deployed these first articles in the field and ran them in an oil and gas operation, and did that for about a year. And the results were really surprising in that sense that these valves outperformed the conventionally deployed valves that were running in parallel to them. So at this point, IIMI said, okay, now we really need to see if you can deliver on your promise and create the same parts on different machines. So what we did is we took out our locked-in golden print file of the first article and sent them to 6 contract manufacturers, 4 of them in the United States, 1 in Europe, 1 in Asia, and had them print these parts again. And this means we have 3 different powder lots, no virgin powder, 6 different printer serial numbers, 6 different manufacturing sites, and we produce the parts and the coupons. So vertical and horizontal tensiles and some specimen for impact testing. And this all went by very smoothly, and very quickly we were able to see our results. So first of all, let's revisit the previously mentioned flow testing. So you can see on the x-axis here the different contract manufacturers, 1, 2, 3, 4, 5, 6, and for each contract manufacturer, the serial number of machine that they have. And what we can see between the minimum and maximum allowable flow, we were actually always well within that range. One thing to note here, and I need to be completely honest, so you may wonder about the first 2 because these are kind of borderline at the maximum allowable limit, but we dug into that and we found out that actually the CM number 1 did some post-processing to the part, some vapor honing process that was actually not agreed or specified, but that opened up the channel a bit and therefore increased the flow rate. What we can take from that is actually, yes, we can control the additive process almost perfectly, but if you don't control or specify your post-processing, you can get in trouble. But overall, we were very happy, and IIMI was very happy with the results here. So next, of course, we also looked again at the witness specimen, the tensile bars. And first of all of them were well above the IIMI design allowable that was specified for the ultimate tensile strength as well as the yield strength. But what is even more astounding to me is that, basically within, I want to say, plus minus 50 megapascals, we were able to achieve consistent mechanical properties on all of these parts. So what does this mean, or what did these results ultimately prove? For IIMI CCI, this is a game changer because they were able to build a part according to API 20S. They were able to prove that repeatability from machine to machine, from deployment side, from production side to production side is possible. And what that means for future production is that now that they have qualified this first design variant, they can very easily now go to all of their other design variants and do a small, cheap, and quick delta qualification and print their parts wherever they need them. So this is the first example that we want to show you today, how our technology helped to achieve that scalability. And now I will hand it back to Gene to talk about another interesting case study, this time not oil and gas, but outer space.
Thanks, Michael. The next opportunity that we explored and study that we proved this capability was with a space propulsion provider who has some really complex but also sensitive material. So we can't quite show the part, but we can show the data. Next slide. So the part you see here is actually a more generic kind of representation of the type of part that we were exploring in this study, and it's one of the flow components in this this type of part that our provider or our OEM was struggling with variability from machine to machine. Legacy AM machines just weren't cutting it with the flow variability that they were seeing, not only from machine to machine, but also supplier to supplier. And we spoke to this this OEM and said, you know, give us a crack at your part and let us prove our capability. So we took the part and sourced it out at 4 different contract manufacturers running 4 different machines and printed the part and then put them into an actual flow test. And what you see here is the Velo 3D flow result versus the legacy manufacturing systems that are out there. And you know, it's not shown, but here's the flow rate is much higher and variable on the legacy machines. Velo 3D is much more tightly packed. And this is an example of the data that comes out with a larger hole size, you know, with scale of about a few millimeters. But this is all done with the technology that we talked about before, the machine health checks, the lockdown process parameters, and the in situ monitoring. Next slide. So here's a little more data showing a much smaller hole size, probably, you know, it's on the scale of several hundred micron hole size. There's inherently a bit more variability because the hole size is much smaller, but Velo 3D still outperformed the competition. And this was again sourced at 4 different contract manufacturers in the same fashion. So it's not just one type of geometry that we're able to pull this off with. It's multiple types of geometries where we see this consistency in machine to machine. Next slide. So moving on from raw data into other parts that have been born into the world of additive manufacturing, scalability on a production regime. And Launcher has been a great customer for us. They've been using our technology to not only unlock design freedom, but also unlock scalability, because what they want to do involves multiple parts over a long period of time. Next slide. The first machine that we're seeing a lot of parts that Launcher is using our technology for is their Engine-2. This is optimized for performance and enabled through additive manufacturing, specifically on the Velo platform. This is one of the highest performing Keralox engines ever made, and really enabled by our technology in the first place. Our ability to print low angles and improve surface finishes. This is something that Launcher saw is hey, it's great right out of the gate, but how do we scale that? And that's where they really see the advantage of printing on a Velo 3D system. Next slide. The pump, the liquid oxygen pump, is it's actually We did a webinar on this a few years back, but the part that you see here is a liquid oxygen pump, part of the engine, that takes liquid oxygen in on the cold side. That's the left portion of the part that was printed in aluminum. There's an internal impeller in Inconel 718, and then on the right side, the darker colored part is the outlet produced in Inconel. And again, this is a little sensitive. We can't show you the inside inner workings of this mechanism. However, these parts are printed on a Velo platform, and they're printed repeatably, reliably through multiple machines. Next slide. Their launcher orbiter is another machine that you'll see several Velo components on. The propellant tanks are not only a fuel reservoir, but also a structural component. So this is another opportunity where Launcher has intuitively designed a part to do more than one function and really optimized for Velo 3D additive capabilities. The tank interior is hollow. There's no supports on the inside, and can be printed multiple times on multiple machines. This is one of their higher demand parts, and they seem to be cranking these out on their machines. The injector and nozzle assemblies are other smaller components, but also produced in a production regime where we have the one print file producing multiple parts, and the turnaround's very quick on this. We can go from design to printing or testing in a short amount of time. Next slide. So as we move through the process of adapting and improving our technology, we've really increased the size and throughput of our machines. To date, we have 4 variants of Sapphire printers. The standard Sapphire is a 2 laser system, and we've expanded a variant up to 1 meter Z. And then the XC is an increased throughput and volume size printer, also available in an XC modification, but we see a great deal of throughput improvement with the 8 laser system. Coming soon, we're developing higher throughput processes, including thicker layers, which will improve our throughput even more so than we already have. And when comparing XC to Sapphire, we see roughly a 4-time throughput increase. And based on these new techniques that we are performing, we expect that throughput to even increase in the near future as well within the next year. And with that, I think we can close out. At this point, we'll take any questions from the audience.
Yeah, thank you, Gene and Michael. As was just said then, we're going to move to the Q&A section, which will feature both of our speakers today. So thank you for all of the questions that have already been sent in. We're going to try to get through as many as we can. And again, those that we don't get to before the time's up today, we'll make sure to get those followed up after the session. So the first one that has come in is, how does this technology differ for different types of companies in different types of industries? So the person who's asked this has given space and energy as 2 examples of different industries. So how does the technology differ for companies operating in those industries?
Well, honestly, in our case, I don't think there is a difference in the manufacturing technology. We manufacture these parts using the same processes, using the same technology, same hardware. It's all the same. What would be different would be the specific way that we go about supporting or adding machine stock, preparing that part for printing. That would be the difference, and we would take that on a case-by-case basis. We have a whole team of applications engineers, tech sales engineers that help our customers on a daily basis examine their geometries and provide feedback and input on what we need to do to a part to make the print outcome successful and desirable, as well as the post-processing that needs to go along with that. So that inherently would vary as well. Do we need to hip the part? Do we need to put it through a post-processing heat treatment to achieve a certain specific material properties or the specifications? If you're doing something for the FAA, you might have to toe the line a little bit more than if you're just printing something like a rocket part or something like that. So the technology is the same. I think the print preparation and implications can vary.
Okay, Michael, do you have anything to add to that?
Yeah, I mean, it's really just the difference is the regulatory framework that you have within the industry that maybe makes it more or less difficult to get a printed part qualified. And some industries are further along, or maybe are not as strict, and other industries are super strict, and the development of such frameworks, requirements, specifications is just still pending.
Okay. Our next question is about cost. So they say, I'd like to use additive manufacturing, but for me, the biggest barrier is cost. So how could they take advantage without having to purchase a machine exactly?
Yeah, so that's a unique thing about another thing that Velo is doing. If you want a printed part, you don't have to buy a machine. We have a network of contract manufacturers. We mentioned them once or twice in this presentation, but owning and operating Velo Sapphires, waiting for opportunities to print parts on a one-off basis or even production basis if that's the need. So we can put you in touch with these contract manufacturers and help nurture that design onto either a one-off or a production level print if you so desire. But you don't have to buy a printer to receive Velo 3D printed parts.
Okay. We've just had one come in, which is how do you measure and understand how much powder reuse can be tolerated versus adding virgin powder?
That's a great question. So I'll give you the loaded engineering answers. It depends. It depends on your alloy. It depends on its affinity for oxygen. We see faster degradation in alloys like titanium and aluminum rather than Inconel or less reactive materials, we'll call it. We are further building a data set on each of those materials and what the allowable lifetime and powder recycling is. Now, that also depends on, like Michael was saying, the regulatory compliance that we need to go through. So some applications might be more stringent to say, I can't allow any oxygen pickup in the powder, so you're stuck using virgin powder every time. There might be an application where it doesn't matter as much. So it really depends, and we would have to take it on a case-by-case basis, but we have data sets showing how the powder does degrade over time.
Okay, Michael, anything to add there?
No.
Okay. Okay, so we've had a few come through. Let me figure out an order here. Do you see an issue with porosity on low angle, no support down-facing surfaces? Do you suggest hipping to collapse porosity?
Let me take that, Gene, this time. Yeah, so that is a very good question. And of course, there's always physics in place. You mean the whole melt pool powder solidification interaction is complex and has a robust process window. Now, I would say with our technology and our process, we can do something unique with very low angle overhangs. So we are able to produce them with very high quality. And by very high quality, I mean better surface roughness than what you can typically see on other systems, and also lower porosity than you can see on other systems if they are not supported. Now, I'm not saying there's no porosity, and I'm not saying that this does not have a negative influence, but we are well aware of the effects that we are seeing. Typically on a downskin, you can look at surface roughness, you can look at keyhole porosity, or you can look at lack of fusion. And we have tested this, and we know that the keyhole porosity, so spherical small pores very close to the contour of the part have a very, very small impact on mechanical properties. Therefore, we have tweaked our process to do just that, to eliminate lack of fusion, to get the best possible surface roughness, but to be still in the robust process range, we have to allow for some small keyholes. Now, depending on your application, if you have high cycle fatigue on your part, let's say an airplane component which might be in service for 20 years, then of course we can explore hipping to collapse these pores. But I also want to throw out there, even if you hip it and you collapse the pores, there is an argument that the pores are still there, they're just not visible. And so always keep that in the back of your mind.
Okay. Michael, I think we have another one for you here. So it's a question from a Mark at Rise Creative Studio, and he says, you mentioned repeatability from multiple sites giving very similar results in testing. Repeatability is closely tied to accuracy and surface finish to achieve these values. What's the best surface finish quality you can achieve, brackets, RA value, on your machines?
Yeah, so it depends, but so depending on the alloy, really. But on a vertical surface, on a vertical wall, or basically perpendicular to the build plate, parallel to the building direction, I think we can achieve down to RA 5 microns or lower. And now, depending on how steep your angle is, your angle of inclination of the surface, that surface roughness gets worse. So on a very low angle, I think we quantified it down to 5 degrees or 3 degrees relative to the horizontal. We are still below RA 20 microns.
Okay. And then the next question we'll go with is, how do you qualify materials and how do you measure or check their properties?
Well, Gene, do you want to take this one now? Yeah.
Yeah. This is a big question, and it depends, and that's something that you need to look at the application, look at what the governing body is, what regulatory body do I need to appease, I'd say, as building a qualification plan. Do I need high cycle fatigue bars, low cycle fatigue, tensils? How big a data set do I need to generate? Then looking at the component itself, what type of testing do I need to do on the component? Do I need to do it multiple times? This is something that's going to be different for each type of qualification that is performed, and it's a bigger question than just pressing a button and say, oh, it's qualified. I wish it were like that. It's just, that's what we're trying to circumvent, a lot of that pain. We can't make it go away entirely, but when we erase the variability that we're talking about today in the inherent processes, it can become much less painful.
Yeah, and I want to add to that. So as Gene said, what we are trying to do is give a high level of confidence that the process parameters are validated and applied to the part in a consistent and repeatable way, then making sure that these command values, these process parameters, are executed properly by our laser powder bed fusion system, and then tying into the metrology that we have and our quality validation system, also making sure that all the key process variables have been intolerant throughout the build. And if you do that, your process was as it's supposed to be. And if you've qualified your process before, you also have a high level of certainty that the mechanical properties will be fine. And now, of course, what sort of tensile specimen and witness specimen you want to include to do destructive testing is really up to the specific application and up to the industry.
Okay. There's a question here about another question about materials. So which materials have been validated to be scalable across different machines and locations?
So honestly, internally, our process for developing a new alloy is a lot of tensile testing, fatigue testing, surface roughness qualification, microstructural analysis, and on an interior or an internal qualification, every alloy that we've released is ready for this scalable production. We don't release process parameters or sets with holes in them or known problems. This is something that any customer can use any one of our process parameters that's available to them to print parts. Now, the unique thing here is if say someone was using a legacy system and developed their own process parameters and said, hey, now I want to go to qualification, and they start that journey, they would be on their own. There's no one other than them working on it. With Velo, we're going to be there every step of the way. If you're going down the production journey, we stand by our product, we stand by our process, and we help provide guidance. And for our customers, that comes at no cost. You know, we don't bill engineering time by the hour. So it's something that we would love to be engaged with our customers and help guide along that process.
Okay, so we've got another one here that I think will, Michael, you'll be able to answer this, I think. So how are thicker layers generated? Is this related to powder granule size or something else?
No, so the powder particle size distribution is stays the same. And the layer thickness is defined by the recoating process. And of course, if you want to do thicker layers, you would just increase the incremental step when lowering the build plate after the lasing before you do the recoat. But the powder particle size distribution will stay unchanged.
Perfect, thank you. There's a question here about the oil and gas case study. So it says, I have not clearly understood if the distributed supply chain analyzed for the oil and gas company considered other manufacturers' machines. So can you clarify whether that was just a Velo study or whether you took into account other machines on the market as well?
I'm not sure here, Gene. Do you know what was done in the beginning before they came to us?
Yeah, I think they did have some frustration with other providers and repeatability, which is why they came to us in the first place. I don't know of any in-depth studies or actual printed parts, but judging from feedback from the customer, there was frustration on the limitation of the inherent technology. Okay,
cool. We had a question asking for Gene and Michael's contact info, so we're just showing the slide of their emails on there. And the next question we will go with, how do you see 3D printing evolving within the tooling market, especially over the next few years?
Yeah, so with tooling, I think in the past, tooling with, for example, maraging steel inserts, conformally cooled, was one of the applications that came first, or that were done in the beginning of laser powder bed fusion, because the regulatory bodies, the specification framework was not as strict in other industries. So if you were just able to produce a part that would fit into your mold and would perform, and by perform I mean do a decent number of shots and maybe decrease cycle time, then it was all good. The problem in the tooling industry is that you need somebody who is controlling the whole process chain. So who is able to design the conformally cooled insert, produce the conformally cooled insert, and then do the molding. So it could be injection molding, it could be aluminum die casting himself. Because for somebody who's just producing the molds or the dies and trying to sell them at a higher price, it's still not that accepted in the industry. However, with the development of laser powder bed fusion and its productivity, cost will go down as well. So I definitely see like a renaissance in conformally cooled, additively manufactured tooling inserts that become more widely accepted in the industry and more a standard.
Okay, thank you. So we've got 5 minutes left, so we probably have time for a couple more questions if some of the audience wants to get any last-minute questions in. I'll also take this time to point out that there's a PDF handout available for download under the handouts section, and this is an engineer's guide to overcoming challenges to scaling metal AM production. Our next question, is any type of post-processing needed for parts produced on the Velo 3D system?
Sorry, was that question, is any post-processing required? Absolutely. Well, okay, let's back up. It depends. If you're making something very simple and don't have critical surface roughnesses or don't need machine threads or don't need to hip or don't need to do these things, theoretically, yeah, you could take something, pop it right off the build plate and be ready to go. I see this more often with bottle openers than anything else. If you have something that is more complex, like a turbine housing or a control valve or something that's going into a real application, I personally have never experienced something that doesn't need post-processing. More often than not, you're going to need it. If you're printing trinkets or show parts or just want a demonstrator, yeah, you could probably get away with little or no post-processing. But if you're including removal from the build plate of post-processing, that's probably, you know, the one thing that is a bare minimum. I know we've claimed in the past that we can free float parts in the powder, but again, that's for mostly like trinket items and small parts, bottle openers, things like that. We haven't found a real world application for free floating parts yet.
Mm-hmm.
Yeah, and I mean, talking about what is post-processing, depowdering is definitely always necessary. I would say in 99% of cases, at least with like nickel-based alloys, titanium, steel, a stress relief is also necessary after you've depowdered the part. But I've also heard like from launcher parts that really have minimum amounts of post-processing. They're basically just depowdered, cut off the plate and shot into space. And it comes all down to how you design the part. What are your design allowables? And if you know them, then you can also design the wall thickness accordingly so that the part will hold as built.
Okay, we maybe have time for one more. So how do you ensure confidence and reliability for parts, and what types of recalibrations are needed? Is it a lengthy recalibration process?
So the reliability in part to part is something that you know we can perform, but then we check by putting tensile bars on the print to double check that we're actually doing what we're claiming we are doing. The second part of the question, sorry, remind me what the second part of the question was.
The second part of the question was about recalibration. So what types of recalibrations are needed, and is it a lengthy process?
Yeah, so that's a great question. On our machine, yes, there are a lot of sensors and sensing equipment. Each one has a cadence as to when it needs to be recalibrated, and there's a procedure to do that, but that's not part of the tool health checks that we perform on as like a weekly cadence. Those are much more quick and easily done. You can do them before each build if you like. We recommend a weekly cadence of running all of these checks. If you do them all back to back, you're looking at an hour or two to run each one in succession. But then you have peace of mind that I'm in focus, my powder bed is healthy, I have no optical contamination. The big heavy hitters that are driving machine variation that we see in the printing process are right there at the fingertips of the technician to check before each build. So the other components that do require some sort of calibration like oxygen sensors, those are a more lengthy time of required calibration between, and we have a spec on each of those as well.
Oh, Sam, you're muted, I think.
Sorry, I am muted. Sorry. So that's probably all we have time for questions. A late question came in about contacting your team. So as an engineer, how would I get in contact if I wanted to speak to your teams?
I would go to velo3d.com. That's the best way to get in touch with an engineer, especially one in your region, and talk about your application, talk about your needs, and go from there. Reaching out directly to Michael and I might not be the best streamlined way to do it, but going to velo3d.com to talk to the proper person in the proper region is probably the best bet.
Perfect, thank you. So yeah, thank you all for your questions. I think there were a few that we didn't manage to get to before time is up, but Velo will follow up with answers to those. Thank you all for joining us. And just to remind you, this webinar will be available on demand within the next couple of days, and you'll be sent a link to access that in case you want to recap on anything you've seen in today's session. Again, a reminder, there's also a PDF handout in the handout section for you to download, so please download that. And on your way out of the session today, there's also going to be a survey. So if you wouldn't mind completing that, would be very grateful. Thank you all again, and we'll see you next time. Cheers.